Hello everybody.
So what is this distribution, two-dimensional distribution? Over here, we shall consider two random variables at a time simultaneously, x and y. We shall consider compound experiments where two random variables are involved, and the joint and distribution function of the random variable is defined in this fashion: f of x comma y, that is equal to probability of minus infinity less than x less than is equal to small x, and minus infinity less than y less than is equal to small y. Hmm. And what is the meaning of this event? Minus infinity less than x less than is equal to small x, and minus infinity less than y less than is equal to small y. In the previous chapters, you already have noticed this idea that over here we actually have a two-dimensional plane, like this kind of two-dimensional plane. There, x and y, small x and small y, it represents a point, maybe this kind of point, small x and small y. Hmm? Now, the meaning of the inequality, that minus infinity less than capital X less than or is equal to small x. It means, say this is our x-axis and this is our positive y-axis. And over here, uh, this much distance over here, this much, if we just draw this much, so this would be our small x, and this would be the position of, over here, this would be the position of y. Rather, we write it over here, this is the position of y. Now minus infinity less than capital X, this is our, you can consider the capital X axis, and this is the capital Y axis. Now capital X, the value of capital X should lie in this zone. Over here, this is minus infinity for capital X, and this should be minus infinity from for capital Y. All right. So it means that when minus infinity less than capital X less than is equal to x, it means that we shall consider this left hand side zone, where this total zone, where this inequality will be satisfied. Again, along with that, we have one more inequality, that minus infinity less than capital Y less than or is equal to small y. What is it? What does it mean? It means that in case of capital Y, this is minus infinity. So over here, if we consider in small y, this is the value of small y. You can say that this would be the straight line. Capital Y is equal to small y. And below this straight line, the inequality, this kind of inequality, below this straight line, this kind of inequality, minus infinity less than capital Y less than or is equal to small y, this kind of inequality will be satisfied. All right. So practically speaking, we are actually interested in an infinite zone, like this kind of infinite zone, and including these regions. Over here, you can consider this kind of regions. Over here, we have minus infinity less than x less than is equal to small x, and in this zone we have minus infinity less than y less than or is equal to small y. So this would be the zone of interest. This would be the zone of interest. And whenever we define capital F of x comma y, capital F of x comma y, this is equal to the probability that minus infinity less than capital X less than is equal to x, comma minus infinity less than y less than is equal to small y. So we are actually considering the probability that this random variable capital X comma capital Y, this two-dimensional random variable capital X comma capital Y, this random variable will lie within this zone. It would not lie outside this zone. It would not lie outside this zone. This is the outside region. All right. So it would not lie outside this region. This is the region of interest. So this probability is defined as a function, and that is the distribution function. We write it distribution function of the two-dimensional random variable. Distribution function of the two-dimensional random variable x and y. The random variable is capital X comma capital Y. The random variables are always designated by capital X and capital Y, and their corresponding real values are denoted by small x and small y. Okay, like this. So this is the idea that over here. This is the definition of the distribution function. And now let's discuss some properties of distribution function. You see, if you consider this kind of inequality, A less than B and C less than D, A less than B and C less than D. Now you see this region, minus infinity to minus infinity less than x less than is equal to b, and minus infinity less than y less than is equal to b. To consider this kind of zone, then what you see, you observe over here. Let me draw the picture over here. Suppose these are the coordinate axis, and over here A is less than B. So suppose this is our small a and this is our small b. All right, and minus infinity less than x less than or is equal to b. So we shall have to consider this kind of line. The left hand side of this zone will designate this left hand side zone will designate this inequality minus infinity less than is equal to x less than is equal to b. And what about minus infinity less than y less than is equal to c? If you consider this much distance, suppose this is the position of c. In that case, b and c, they will intersect over here. So this is the point having coordinates b, comma c. All right, this is the point having coordinates b, comma c. So minus infinity less than x less than is equal to b, and minus infinity less than y less than is equal to c. This will represent this kind of zone. This kind of zone. Okay. This kind of zone. Is it clear so far? Dekho. Is this much clear?
Yes, sir.
Okay. So now you see this zone can be, you can extend it over here in this part and in this part. So now you see this zone can be divided into two zones. This is one zone. This is a zone. This is one zone. And what is this? This zone can be written as minus infinity less than x less than is equal to a. Why less than is equal to a? Because over here this is the straight line. This is the straight line, x is equal to a. This is the straight line x is equal to a, and of course minus infinity less than c less than y less than is equal to c is there. It means that we shall have to consider the region below this straight line y is equal to c. And what is the remaining zone? This is the remaining zone. Over here you can see that this is actually infinitely extended in downwards side, infinitely extended region. So this infinitely extended region is actually bounded by these two lines. This x is equal to a and this is x is equal to b. So we can say, you see, x is equal to a. This equality has been chosen over here in this zone. So the remaining part would be less than is equal to strictly less than is strictly less than inequality. So a less than x less than is equal to b. Got it? So this is the zone that a less than capital X less than or is equal to b, because x is equal to a has been included in this first zone. So we have this second zone minus a less than x less than is equal to b. And what about y? What is the restriction on y? The restriction is this one, minus infinity less than y less than is equal to c. This was the restriction. That means we should have to consider this this portion just below the line y is equal to c. This is the line y is equal to c, or capital Y is equal to c. We should write capital Y is equal to c. So this is the zone below capital Y is equal to c, and that will be designated by this kind of inequality, that minus infinity less than y less than or is equal to c. So it is clear that this entire zone can be divided into two portions, and this region, this total region, will designate one event, and this second region, this will designate the second event, and both of these two are disjoint, or you can say that mutually exclusive. That's why I'm just removing this picture. That's why you see this is the first zone, the zone represented by the inequality, and the second zone is represented by this kind of inequality, and their total union has been taken over here as equal to this summation symbol. All right, this total union has been represented by this kind of inequality. And this is a mutually disjoint union of two mutually exclusive events. All right. So what we can say, if we now say consider probability of if we consider the probability of this right hand side event, then probability of this right hand side event must be equal to the probability of first event plus the probability of second event by the third axiom of probability. What is the third axiom? The third axiom says that if we have two events, one is A, another is B, such that they are mutually exclusive, then probability of A union B, or A plus B, whatever you call, that would be is equal to probability of A plus probability of B. Got it? So applying this third axiom, we got this result, that probability of this event that must be equal to the probability of this event plus probability of this event. But what is the probability of this event? Probability of this event, if you look at the definition of probability distribution function, you see minus infinity less than capital X less than is equal to small x, and minus infinity less than capital Y less than is equal to small y. So in place of small x and small y, we have small a and small c. Therefore, this probability must be is equal to probability distribution function, value of the probability distribution function at the point A, comma C. Got it? That's why over here in the next line you see it has been written as equal to f of A, comma C. Similarly, if you consider the probability of this second event, this probability of second event would be is equal to value of the probability distribution function at the point B and comma B and C. So this would be the value of the probability distribution function at the point B comma C. That's why we have written this f of B comma C. All right, and the middle this probability remains same. You see probability of this event. What we find is that from this result, we find that probability of this event can be written as this probability of B comma C minus and this f of B comma C minus f of A comma C. All right. So that this is the result that we shall use frequently in future. We shall use frequently in future probability of this kind of event. You can see that A less than X less than is equal to B. No such no such restriction is there. Only restriction is there on C. So we have C over here. In place of Y, the upper bound is C. That's why you see in the Y coordinate we have C and C over here, and in the X coordinates A less than B. So B minus C. This is B, f of B comma C minus f of A comma C. So in this way you can remember this kind of formula, and similar kind of formula holds if you consider a region where C less than D less than Y less than is equal to D. C less than Y less than is equal to D. Over here, of course, C is less than D. Got it? You see over here the upper bound is A. So in the X coordinate f of A, and over here this is also f of A. So A remains fixed. And the larger quantity is D. The smaller quantity is C with respect to Y. That's why in the Y coordinate D f of A comma D minus f of A comma C. So these are the two results that you need to remember in order to proceed further. These two results you need to remember. And along with these two results, you see this is the probability. We know that probability can never be less than 0. See, it is always greater than is equal to 0. So as because it is greater than is equal to 0, therefore we can say that this left hand side term must be greater than is equal to this kind of term. So f of B comma C must be greater than is equal to f of A comma C. All right, f of B comma C. I think we have a mistake over there. It would be it is a mistake. It would be greater than symbol. This is a mistake. Be a bit careful. F of B comma C would be greater than f of A comma C. Over here, this second part is correct. This is correctly written. This is greater than or is equal to sign may appear because this probability is greater than is equal to C. So similarly, this one is also greater than is equal to 0. That's why this kind of inequality comes. So this is about the probability distribution function. So what we find in this probability distribution function is that over in this region, sorry, this should be greater than or is equal to 0. Over here, A is less than B, or you can say that B is greater than A. So if B is greater than A, then f of B comma C should be greater than or is equal to f of A comma C. Similarly, over here, D is greater than or is equal to C. Alright, this D is greater than or is equal to C. So f of A comma D is second coordinate, variation in the second coordinate. F of D A comma D is greater than or is equal to f of A comma C. So this kind of variation occurs in case of distribution function. So you can say if you forget about this first coordinate, you can say you see D is greater than C. That's why f of D is greater than f of C. So you can say that f is monotone increasing. In fact, strictly monotone increasing, not strictly because equality comes. Or you can say that it is not monotone. It is monotone non-decreasing function with respect to this second coordinate. Similarly, with respect to this first coordinate as well, over here is greater than is equal to symbol of term when B is greater than C. So we can say that this distribution function is monotone non-decreasing with respect to the first coordinate, that is x coordinate. That's why we can say that this function f is monotone non-decreasing in both of these two variables x and y. Alright. So the function distribution function is always a monotone non-decreasing function. And you can consider this kind of regions where semi open rectangular region or half open rectangular region where a less than x less than is equal to b. Over here open inequality is there, or equality does not occur over here. Similarly, c less than y less than is equal to d. Over here this y is equal to c, this equality does not occur. And in such cases, we can prove from the previous results that probability of this kind of zone. You see, if you look at this carefully, there is a small gap over here. Just to describe that, A is strictly less than x and C is strictly less than y. Over here, this is the zone that has not been covered. So this kind of region is designated by this kind of dotted or shaded region. All right. So from the previous definition, one can prove that probability of A less than x less than is equal to b and c less than y less than is equal to d. This probability must be is equal to this kind of expression. Now, how to remember this kind of expression? You see f of b comma d. This is the point. B comma D plus f of a comma c. F of a comma c. So if you consider this kind of matrix where these are the elements, this is one element, this is second element, this is third element, and this is fourth element. In this kind of matrix, in that case, you can say that this is actually the cross diagonal, and this is the main diagonal elements. These are the main diagonal elements. So along the cross diagonal elements, this from this portion at this point b comma d, we have a positive contribution. Similarly, at the point a comma c, we have a positive contribution. All right, and along the main diagonal, along this main diagonal, at the point a comma d, we have this kind of negative contribution. Similarly, at the point b comma c, we have this kind of negative contribution. So you can remember the formula in this way, that along the cross diagonal elements, the positive contribution is there, and along the main diagonal elements, we get negative contributions. Okay. So in this way, you can remember the formula, that probability A less than x less than is equal to b, and c less than y less than is equal to d is equal to this kind of expression. And in this expression, you see, if you in this definition, not in this expression actually, I would say, in this definition, where is this definition? In this definition, minus infinity less than x less than is equal to capital X. What was the region? I told you. You see, I made a drawing over there. This kind of region. Now, in this kind of region, if you take the limit extending to minus infinity, if you take the limit extending to minus infinity, then what happens? If x tends to minus infinity, in that case, you can say that x tending to minus infinity. Then you see this line. This is the line. This is the line. Capital X is equal to small x, and it is moving towards left hand side. Okay, it is moving towards left hand side. Capital X is equal to small x. This line is moving towards left hand side. Then at the limiting position, what we have? At the limiting position, what we have? At the limiting position, this line, this would be the position of the line. Might be, you can say that as you take the limit x tending to minus infinity, then what we have? We do not practically have any line at all. This zone will get decreased. Ultimately, it will be equal to an empty set. this zone will not contain any point at all. X tending to minus infinity means it is moving along left hand side. So this is the zone where we would not have any region at all. So what would be the contribution from this inequality? Minus infinity less than x less than is equal to small x with the limit that small x tending to minus infinity. So if you consider this limit small x tending to minus infinity, then this left hand side and right hand side, both of these two limits would be same, and in that case we have only one element, x is equal to the empty set or an impossible event. So ultimately we will encounter an impossible event. Got it? That's why in the result what we have this type of definition, f of x comma y, that is equal to probability that minus infinity less than capital X less than is equal to small x, and minus infinity less than capital Y less than or is equal to small y. So if you take the limit, if you take the limit x tending to minus infinity, in that case what we shall have? We shall have f of minus infinity comma y. That would be is equal to probability that minus infinity less than capital X less than is equal to minus infinity comma minus infinity less than y less than is equal to small y. But you see, this zone is actually, what does it mean? It means that we should say that probability x is equal to minus infinity. And the second part will remain same, minus infinity less than y less than or is equal to small y. But you see, x is a random variable. A random variable always assumes real values, so it cannot assume minus infinity. It is an extended real number. Therefore we can say that this is actually not possible. So this kind of event will mean an impossible event. Therefore it would be an impossible event. Probability of that impossible event is equal to 0. So what we have, f of minus infinity comma y is equal to 0. Similarly, if you consider the limit y tending to minus infinity, in that case also we shall have f of x comma minus infinity, that is also equal to, sorry, that is also equal to 0. All right. So we have these two results that says that f of minus infinity comma x, sorry, f of minus infinity comma y, this one, f of minus infinity comma y is equal to 0, and f of x comma minus infinity is equal to 0. All right. But you see, if you consider this kind of limit, x tending to infinity and y tending to infinity. But before that, let me complete the previous discussion first. We had this type of result, f of minus infinity comma y is equal to 0, and we had one more result, that f of what, x comma minus infinity, that is also 0. So further over here, further in this region, on these results, if we further take the limit, y tending to plus or minus infinity, whatever kind of limit you want to consider, if you further take the limit y tending to say plus infinity or minus infinity, it doesn't matter. Y tending, so firstly, if you take y tending to plus infinity, in that case also what we shall have, then we shall have f of minus infinity comma infinity, that would be is equal to 0, because the over here the right hand side, this right hand side portion this right hand side portion, is equal to 0. This right hand side portion is equal to 0. So again, if you take y tending to the limit minus infinity, in that case also, what we shall have, f of minus infinity comma minus infinity, that is also 0. So over here again, you can also take the limit extending to plus infinity or minus infinity. In that case also you will get this type of result. Say f of infinity comma minus infinity is equal to 0. So you see, out of these results, if any one component, if at least one component of at least one value of x or y becomes is equal to minus infinity, in that case the value of this distribution function is equal to 0. But what happens if both of them are infinity? What is the value of f of infinity comma infinity? Alright, I am going to address this question. What is the value of f of infinity comma infinity? The answer is that this value would be is equal to 1. Why? Because you see, I told you that if you consider this kind of two-dimensional plane, say this is capital X axis and this is capital Y axis, and this is the zone. This is the zone. This is the zone where we have the definition f of x comma y, that is equal to the probability of this kind of region minus infinity less than capital X less than is equal to small x, and minus infinity less than y less than or is equal to small one. Now, if you further take the limit, this is the straight line, capital X is equal to small x, and this is the straight line, capital Y is equal to small y. So, if you take the limit extending to infinity, and then along with that y is also tending to infinity, small x tending to infinity and small y tending to infinity. In that case, after taking the limit, let me write it in a by this kind of color. If you take the limit as extending to infinity and y tending to infinity, then on the left hand side we will get this type of relation, this type of result. In that case, we shall have f of infinity comma infinity, and that would be is equal to probability minus infinity less than capital X less than or is equal to infinity, comma over here minus infinity less than capital Y less than is equal to infinity. And what is this? This is actually the probability of certain event, because in two-dimensional plane, this entire two-dimensional plane will give us the certain event. So we can say that that is actually the probability of the entire two-dimensional plane, and that probability is equal to 1. Got it? So in this fashion, the probability is equal to 1. So in this fashion, we can say that the probability that minus f of infinity comma infinity is equal to 1. So if we summarize all these results, what we got this result. Number one, that f of minus infinity comma y is equal to 0. Whether y is finite or infinite, it doesn't matter. Then f of say x comma minus infinity, that is also 0. Whether x is finite or infinite, it doesn't matter. Then we have this result that f of minus infinity comma infinity, that is also 0. Then f of infinity comma minus infinity, that is equal to 0. Next, f of minus infinity comma minus infinity is equal to 0. And finally, we have this type of result that f of infinity comma infinity, that is equal to 1. So we have all these results. Now the next question that comes in our mind is that what would be the value of this type of expression? Suppose we have infinity in one coordinate. Suppose the value of x is equal to infinity, and the value of another coordinate is a finite quantity. Similarly, f of x is there, a finite quantity, and the value of another quantity is equal to infinity. Then what happens? What are the values of this kind of quantities? And we can prove that this kind of quantities are actually related to another idea that is called the marginal distribution. I am coming to the idea of marginal distribution, but is this much clear to you, everybody? Hello?
Yes, sir.
Do you have any question from this portion?
No,
Any kind
sir.
of question? No question.
No, sir.
All right. So let me start with this idea of marginal distribution. What is marginal distribution? The marginal distribution says that if we say, suppose if we consider this limit extending to plus infinity, and if we fix this value of y at certain finite value, hmm, and in that case we can say that this is actually a function of y alone, not a function of x. And it has been generated from this two-dimensional function f of x comma y. All right. So we could write this function by say g of y, maybe something like that. We could write it in this fashion, g of y. But instead of writing g of y, we rather consider, we rather write this function g is equal to the function f, is equal to the function f suffix y. What does it mean? Remember, it does not mean the partial derivative. It just means that we are actually generating this function g from the original two-dimensional function f. That's why we have used this notation capital F, and this capital F is uh, is actually a function of y. And that's why we have this kind of value y, and therefore we can write this expression as equal to f y at the point, at which point maybe y is equal to y0 or y1 or y2, but in general at the point y we write it in this way. So if we put over here, say if we put say y is equal to 1, in that case how to write? In that case we should write that from this line, from this line what we would get this kind of result, that f of infinity comma 1, we shall designate it by f suffix y at the point 1. So by just putting y is equal to 1, don't ever change this suffix. Just this suffix designates that this is actually a function of y. And what is the value of the function? The value of the function is to be written at this point. Alright, fy at the point 1. So this is, sometimes you make mistake that you also put y is equal to 1 over here. So don't put y is equal to 1. This is just a notation. This altogether f suffix y is the function. So function should not be changed. The value of the corresponding variable should be changed. So if you put y is equal to 1 over here, you should put y is equal to 1 within this bracket, not within at the suffix. Similarly, this expression, this one should be, we write it in this way, fx computed at the point x. So again, if you put x is equal to 2, so if you put x is equal to 2 over here, x is equal to 2, in that case how to write? If 2 comma infinity, that would be f suffix x computed at the point 2. And one can prove, one can show that these functions, these functions, these functions satisfies all the properties of a distribution function. What are the properties of a distribution function? The properties are that firstly, this function should be monotone non-decreasing function, and you see, let me write it to once again, although it has been discussed in the previous classes. This f, if you consider this as a function of single variable, in place of f rather let us write h. Suppose h is a distribution function of certain random variable. In that case, h, number one, it should be monotone non-decreasing, monotone non-decreasing, non-decreasing. Then the second property is that h of infinity or h of minus infinity is equal to 0. Third property is that h of infinity is equal to 1. All right, monotone, non-decreasing, and secondly, it is bounded. I mean to say that the maximum value of h would be is equal to 1. Monotone, non-decreasing, the maximum value of h is equal to 1, and the minimum value is equal to 0. All right. So these are the properties of distribution function, and you can check over here. You can check that this function, this fy and this function fx, both of these two functions are monotone. All of them are over here. All of them are monotone, non-decreasing. H of minus infinity is equal to 0, and they satisfy this kind of property. And one more property I forgot to mention, that it is continuous on the right. You can check, it may have left discontinuity, but it is continuous on the right, on the right side. That means it is always right continuous. What does it mean? It means that h of x plus 0, the right limit, that will be is equal to h of x for all value of x. That is the right continuity. It may have certain left discontinuity. That means at certain point it may be that h of x minus 0 is not equal to h of x. You can check that all these four properties are satisfied by these functions f suffix y and f suffix x, and that's why we can say that these two functions f suffix x and f suffix y, these two functions designate certain kind of distribution function, and the corresponding distributions are called marginal distributions. Marginal. Corresponding distributions, let me write it over here. Corresponding distributions are called marginal distributions. So we have the marginal distribution of x, marginal distribution. Let me write it in shortcut like this: marginal distribution. Marginal distribution of x is actually designated, is obtained by this kind of function. So what is this? That is, the definition is that f of x suffix x of x is equal to the quantity f of x comma infinity. So this gives us the marginal distribution. And why marginal? Because it is obtained from the distribution of a two-dimensional random variable. Similarly, this is called the marginal distribution of the random variable x. Similarly, you can consider the marginal distribution of y, that is obtained by this kind of function f suffix y of y, and that is equal to f of infinity comma y. Alright, so this is the marginal distribution of y. Now, is it clear, everybody? Marginal distribution.
Yes, sir.
So we have discussed this marginal distribution of x and marginal distribution of y, and now we shall define independent random variables. Independent random variables. We say that two random variables, capital X and capital Y. Capital X and capital Y, these two random variables are independent random variables whenever probability of this type of interval minus infinity less than x less than is equal to small x, and minus infinity less than y less than is equal to small y, whenever the probability obtained from this joint probability distribution that becomes is equal to the product of individual probabilities. Probability that minus infinity less than x less than is equal to x, probability that minus infinity less than y less than is equal to. And I forgot to mention that in case we defined this marginal distribution f of fx of x, what was this? That was actually partial, this kind of expression, f of x comma infinity. So in terms of probability, if you write it in this way, that would be probability of for this first coordinate minus infinity less than capital X less than or is equal to small x, comma minus infinity less than y less than is equal to, this plus infinity should come over here. Alright, and what is this? Minus infinity less than y less than is equal to capital Y. In terms of capital Y, this is actually a certain event, just this much. So whatever kind of value you take, it would always lie in this interval minus infinity less than x less than is equal to y. So we can simply write it this one in this fashion: probability that minus infinity less than capital X less than is equal to small x. Make it clear. Minus infinity less than capital X less than or is equal to small x. You don't need to explicitly write the value of y, because you know that y is the value of y always lies in the certain event. So this expression, that probability minus infinity less than x less than is equal to small x, that would be the value of this marginal distribution function f of x comma x. That's why this expression over here, this expression can be replaced by this kind of expression f suffix x of x. This is the expression. And similarly, this expression probability that minus infinity less than y less than minus infinity less than capital Y less than is equal to small y, this should be replaced by corresponding marginal distributions. So equivalently, we can say that this is the distribution function obtained from the joint probability distribution, and these are the values of the marginal distributions. Alright. So if we say that two variables x and y are independent random variables, provided the joint distribution can be written as the product of two marginal distributions. This is the definition. We can have the example of different distributions in which the random variables x and y are not independent at all. We shall come and discuss this kind of examples in the subsequent lectures. But over here, this is the definition. And this kind of definition has some other kind of consequences. You see, this is the theorem, a very easy theorem, more or less about 2 or 3 marks can be given in exam in order to prove this result. What does it say? It says that a necessary and sufficient condition for the independence of the random variables x and y is that their joint distribution function, their joint distribution function f of x comma y, this expression can be written as the product of a function of x alone. One should be a function of x alone and another would be a function of y alone, just like this. You see, if x and y are independent, then this is a function of x alone. This expression is a function of x, only a single variable x. And similarly, this expression is a function of y only. But what about the converse? Converse should be proved. That means, suppose f of x comma y, this f of x comma y, that would be is equal to a product of a function. Over here, this is a function of x only, and this is a function of y only. We shall have to prove that in such case, if this distribution function can be represented as a product of only a single variable x and only a single variable y, in that case, this is a distribution function. And in that case, this capital X and capital Y, these two random variables will be independent of each other. Okay. Now, how to show this result? You see, we have a result that f of infinity comma infinity is equal to 1. We have this result. So from this result, if you take the limit, both over here x tending to plus infinity and y is also tending to plus infinity, then on the left hand side, what we shall have? On the left hand side, we shall have this type of expression f of infinity comma infinity, and this value should be is equal to 1. And on the right hand side, this expression g of x is to be replaced by infinity, so we shall have g of infinity and multiplied by h of infinity. So we have this result that g of infinity multiplied by h of infinity is equal to 1. So this value is equal to 1. Therefore, if we have this result, f of x comma y is equal to 8 gx into hy. So if we divide this expression by 1 means this quantity, g of infinity multiplied by h of infinity. Then on the left hand side, we actually have this function of x comma y. Alright, so this f of x comma y, you can consider this line, this f of x comma y can be considered is equal to g of x divided by g of infinity. Over here you see g of x divided by g of infinity multiplied by h of y divided by h of infinity. And therefore you see, therefore if you not take the limit as say y tending to infinity, you take the limit as y tending to infinity, then what we have, y tending to infinity means we shall have f of x comma infinity, and that is nothing but is equal to the marginal distribution function fxx. So fxx is equal to f of x comma infinity, and after taking the limit as y tending to infinity, what we shall have over here, h of infinity divided by h of infinity. So this h of infinity and this h of infinity will get cancelled. Ultimately, we shall have g of x divided by g of infinity, and that would be is equal to this this marginal distribution function fxx. Similarly, we can prove that this fyy is equal to h of infinity divided by h of y divided by h of infinity. So what we have, this first factor is equal to our f x, and this second factor is equal to f y, y, and that is the definition of independence of the random variables capital X and capital Y. So joint distribution function has been written as the product of marginal distribution functions. So we can say that in this case, capital X and capital Y are independent random variables. Therefore, it is sufficient to prove that the joint distribution function is a product of a function of variable X and the function of the variable Y. In that case, we can directly conclude that yes, capital X and capital Y are independent of each other. Yes. So this is one property that is satisfied. And if you have this type of property, in that case, you see in case of independent random variables, this f of b comma d, you see all such properties. You see we have this type of result: f of a less than x less than is equal to b, c less than y less than is equal to d, and that can be written by this type of expression I told you earlier. Now this f of b comma d, in case of independent random variables, this can be written as f of b multiplied by f of d. But over here, this would be the fx and this would be fy, the marginal distribution functions. Similarly, all the terms can be factorized in this way. And if you factorize all these terms and make the calculations, in that case, you see this quantity, this kind of quantity, or this right hand side, particularly speaking, this right hand side can be written as this kind of product, where product a less than x less than is equal to b, and c less than y less than is equal to b. This is the expression: probability a less than x less than is equal to b, and probability c less than x less than is equal to b. Therefore, in case of independent random variables, you can write this probability is equal to the product of individual probabilities of x and y. Even at a particular point, if you in this example, if you take the limit b tending to a and d tending to c, in that case, this expression would be probability that x is equal to a. This is the expression: probability that x is equal to a or x is equal to b. Similarly, probability of y is equal to c or y is equal to d, whatever you write, like this. And in that case, this would be x is equal to b, and this would be y is equal to d. So you will get this type of relation. So these three properties has to be used whenever we have independent random variables. That this much I wanted to discuss in this class. So that's all for this lecture. Thank you for being with us.